In this presentation, I'll be presenting our paper, Trajectory Optimization in Learned Multimodal Dynamical Systems via Latent-ODE Collocation. The goal of our work is to find trajectories in unknown or partially unknown multimodal dynamical systems that attempt to remain in a preferred dynamics mode. Now, this might be because some of the dynamics modes aren't operatable, maybe they're not safe, or maybe they're not efficient. But for whatever reason, we would like to remain in our preferred dynamics mode. And given that we'll be learning our dynamics model from a historical data set, we would also like to avoid regions of dynamics that have not been observed. And this is because they cannot be predicted confidently. So whenever we learn a model from data and we wish to make predictions, we cannot be confident in our predictions as we extrapolate away from our data. This concept is known as epistemic uncertainty, and it is reduced in the limit of infinite data. Our method is tested on a velocity-controlled quadcopter example, subject to spatially varying turbulence. This figure shows a top-down view of our environment, where a fan has been placed at the side of a room, which has induced a turbulent dynamics mode in front of it. And the green region shows a non-turbulent dynamics mode governing everywhere else in our state space. Now, given a start and end location in our room, we would like to find trajectories that remain in our non-turbulent dynamics mode. And given that we have not observed a subset of our environment, we would also like to avoid entering this region. More formally, we have a two-dimensional space consisting of x and y coordinates, and we are considering a velocity-controlled experiment. The bottom left shows our multimodal transition dynamics, consisting of k transition dynamics functions fk, which map the state and control at a given time to the state derivative. Importantly, we have our mode indicator variable alpha, which indicates which dynamics mode governs the dynamics at a given time step. In our example, as the dynamics mode varies spatially over our state space, we formulate a spatially varying probability distribution over alpha so that we're able to infer this structure from observations. Our method is a two-stage approach. In the first stage, we learn a probabilistic transition dynamics model from a historical dataset, with a model resembling a mixture of Gaussian process experts model with a Gaussian process-based gating network. We derive a variational inference scheme based on sparse GP approximations, which provides scalability for our model. In the second stage, we exploit some of the geometric structure inferred by our transition dynamics model to encode our goals into an objective function. We then observe that our objective function parameterizes geodesic trajectories, and we exploit a classic result of Riemannian geometry and implicitly minimize our objective function by projecting our trajectory optimization onto the geodesic ODE, whose solutions implicitly minimize our objective. We then solve this geodesic ODE using direct collocation, which allows us to transcribe our optimal control problem into a nonlinear program. So, in the first stage of our method, we learn a probabilistic transition dynamics model, whose graphical model is shown here. X hat represents the state and control at time t-1, and the graphical model shows a latent process that generates a change in state between time t-1 and time t. Note that this is a discrete time representation of the dynamics that was shown previously. On the left in the orange are the k dynamics modes, where we've placed a Gaussian process prior on each of the transition dynamics functions. The process noise in each mode has been modeled with a Gaussian likelihood, whose noise variance term is shown here. Now, of particular importance is a gating network on the right-hand side. Here, we have a set of k gating functions, hk, and we normalize their output to obtain a discrete probability distribution over our mode indicator variable alpha, which tells us the probability that a particular dynamics mode is responsible for predicting at a given input location. When a particular gating function is high, that indicates it believes its associated dynamics mode is responsible for predicting at that input location. and when it is low, it believes it does not. As we would also like to know when our gating function doesn't know, that is, when it can't predict confidently, we place GP priors on each of our gating functions so that we can use the posterior covariance as a quantitative value to represent our epistemic uncertainty, which we can then exploit in our trajectory optimization. Evaluating the marginal likelihood of this model is extremely computationally intensive due to each GP depending on all of the observations in the training set. For this reason, we augment our probability model with a set of inducing points for each GP. And we use this sparse GP approximation to derive a variational lower bound, which can be optimized with stochastic gradient methods, which significantly improves scalability in the mixture of Gaussian process experts model when using a Gaussian process-based gating network. This figure shows a GP posterior over our desired mode gating function. The left shows the posterior mean, and the right shows the posterior variance. We can see that the posterior mean is high in our desired dynamics mode and low in the turbulent dynamics mode. So this is super neat. We've learned a factorized representation over our underlying dynamics modes. We can also see that the posterior variance has clearly captured information regarding where we've observed data. Where we have observed data, the posterior variance is low, and where we have not, it is high. So it's really neat. We have a quantitative value which represents our epistemic uncertainty. So given our start and end locations, we would like to find trajectories that remain in our desired dynamics mode. And this is equivalent to finding shortest trajectories on this manifold parameterized by our desired mode gating function. So based on this intuition, we formulate a geometric objective function which finds shortest trajectories. And then we extend our geometric objective function to probabilistic geometries to also include information regarding the posterior variance. In the second stage of our method, we perform trajectory optimization using our learned transition dynamics model. In trajectory optimization, it's common to encode our goals into an objective function. In our problem, we have two goals, so we formulate an objective function with two terms. The G mode term encodes our goal of remaining in our desired dynamics mode, and the G epistemic term encodes our goal of remaining in regions of dynamics which have been observed and can be predicted confidently. We then wish to minimize this objective function, subject to our transition dynamics and our boundary conditions. We'll now formulate the G mode term based on the geometry of the desired mode gating function and the intuition that finding shortest trajectories encodes our goal. So our desired mode gating function maps from our state space to the set of real numbers, and we have a state trajectory in a given time interval. We can calculate the length of this trajectory in our state space by simply integrating the Euclidean norm of the velocity over our trajectory. However, we are not directly interested in the length of our trajectory in the state space. We are interested in its length on the manifold parameterized by the gating function. So let's simply map our trajectory through the function and follow the same approach. So here we have the derivative of our function with respect to time. And we exploit the chain rule, and we take the derivative of our function with respect to its input, the Jacobian, and then we take the derivative of our input with respect to time. Now, this is super cool because what we have now is a locally defined norm. And here we have GXT, which is known as a Riemannian metric tensor. And with this Riemannian metric tensor, we are able to calculate lengths on our manifold in our input space. We can then formulate a geometric objective function which encodes a G mode term as length minimizing trajectories using this metric tensor, shown in equation 5. Now then, how do we encode the G epistemic term? So we first remember that the differential operator is linear, which means that the derivative of a GP is also a GP, given that the mean and covariance functions are differentiable. And we had that our Riemannian metric tensor is given by the product of the Jacobians, and this induces a non-central Fisher distribution over it. Now, importantly, in equation 8, the expected value of this metric tensor contains a covariance term, the covariance of the Jacobian. Now, calculating lengths with the expected value of this metric tensor will increase in areas of high covariance. Now, this is super cool because this encodes our G epistemic term and will encourage trajectories, which are length minimizing curves, to remain in regions of dynamics which have been observed and can be predicted confidently. Now that we have this expected metric tensor, we can sub this back into our objective function and solve our trajectory optimization problem. We observe that our geometric objective function parameterizes geodesic trajectories. A classic result of Riemannian geometry is that geodesic trajectories are solutions to the second order continuous time ODE shown here. As such, we solve this second order ODE subject to our boundary conditions, and by doing so, implicitly minimize our geometric objective function. We solve the geodesic ODE using Hermite-Simpson collocation. We first discretize our trajectory into a set of collocation points. We then define a set of collocation constraints at the midpoints, which we use as constraints in the sequential least squares programming optimizer in SciPy, with a dummy cost function. The result of the optimization is the blue line shown here, which is pretty cool. We have been able to remain in our preferred dynamics mode, and we've also been able to remain in regions of dynamics where we can predict confidently. We avoid going to this region of high posterior variance. Thank you very much for listening.